Mars Climate Orbiter Failure Board Release Report. Numerous NASA actions underway in response. What is the report all about? The report is focused on the failure of the Mars Climate Orbiter mission and the subsequent actions taken by NASA's Jet Propulsion Laboratory or JPL in response to the loss. It provides insights into the findings of the mission failure investigation board's initial report. The Mars Climate Orbiter was a spacecraft designed to study the climate and atmosphere of Mars. However, it experienced a mission failure due to various contributing factors which are discussed in the report. What are the issues of the case? The report highlights several critical issues that led to the loss of the spacecraft. These include inadequate consideration of the entire mission as a total system. The report emphasizes the need for a comprehensive understanding of the mission and its post-launch operations, including factors such as navigation, communication, and verification processes. Inconsistent communications and training. The project suffered from shortcomings in communication and training within the team. This lack of clarity and knowledge transfer contributed to the errors and misunderstandings that occurred. Lack of complete verification of navigation software and computer models. The failure board identified deficiencies in the verification process, particularly regarding the navigation software and associated computer models. Insufficient checks allowed the errors to go unnoticed, leading to the incorrect predictions and critical mistakes. Undetected errors in ground-based computer models. Errors in the models used to predict and execute small thruster firings during the spacecraft journey to Mars were not identified in time. This oversight resulted in deviations from the intended path. Insufficient systems engineering function. The project system engineering function responsible for overseeing and double-checking interconnected aspects of the mission was found to be lacking. This deficiency was exacerbated exacerbated by the handover of the spacecraft from the construction and launch team to a new operation team, resulting in gaps and oversights. Informal communication channels. The report indicates that some communication channels among project engineering groups were too informal, leading to potential misunderstanding and incomplete information transfer. Lack of peer review for the navigation team's work. The small mission navigation team did not receive adequate peer review from independent experts, which could have identified and rectified potential errors or issues. Insufficient training and process familiarity. Personnel involved in the mission were not adequately trained in critical areas, such as the relationship between mission operations and navigational characteristics, or the process of filing formal anomaly reports. This knowledge gap contributed to the mishaps and lack of appropriate actions. Inadequate verification and validation processes. The report highlighted flaws in verifying and validating certain engineering requirements and technical interfaces between project groups and the prime mission contractor. This inadequate process compromised the overall reliability and robustness of the mission. How NASA addressed the issues. NASA addressed the issues identified in the report through a series of actions aimed to preventing similar incidents in the future. The key steps taken by JPL include assignment of a senior management leader. A senior figure was appointed to provide oversight and strategic guidance for the ongoing missions and to ensure that the necessary corrective actions were implemented effectively. Review and augmentation of work plans. The work plans were thoroughly reviewed and revised, considering the lessons learned from the failure. This ensured that all critical aspects of the mission were adequately addressed. Detailed fault tree analysis. In-depth fault tree analysis were conducted for upcoming mission events to identify potential risks and mitigate them proactively. This comprehensive approach allowed for a better understanding of potential failure modes and the development of appropriate preventive measures. Daily teleconferences and technical progress evaluations. Regular teleconferences were established to evaluate technical progress, identify challenges, and plan the necessary work to be done. This improved communication and collaboration among team members, increased availability of the deep space network, which facilitates communication with spacecraft, was made more readily available to ensure robust and reliable communication links with the spacecraft. Independent peer review. To enhance quality assurance, all operational and contingency procedures underwent independent peer review. This process involved experts external to the project, who assessed and approved the proposed actions. How important is the knowledge of embedded systems in space technology? Knowledge of embedded systems is of paramount importance in space technology. Embedded systems play a crucial role in spacecraft as they are responsible for various critical functions such as navigation, propulsion, communication, and data processing. The failure of the Mars Climate Orbiter mission was attributed to a software error resulting from a failed translation of English units into metric units. This incident underscores the significance of accurate and reliable embedded systems in space missions. Any inaccuracies or failures in these systems can have severe consequences for the success and safety of the spacecraft. Precise measurements, calculations, and units are fundamental in space exploration. Engineers working on space missions must have a deep understanding of embedded systems and ensure their robustness, accuracy, and compatibility with the mission requirement. What what are your what are your takeaway learning as a computer engineer based on this case? As a computer engineer, this case provides several important takeaways. Thorough verification and validation processes are essential to catch and rectify errors before they become critical to mission success. Rigorous testing, peer review, and independent scrutiny can help identify and address potential issues early on. Clear and consistent communication among project teams is vital to ensure that everyone has the necessary information to perform their task accurately. Formal channels of communication and documentation must be established and followed. System engineering plays a crucial role in overseeing and double-checking all interconnected aspects of a mission. A robust system engineering function can help prevent errors and improve overall mission success by ensuring that all components and processes work seamlessly together. Proper training of personnel is essential to ensure a deep understanding of mission operations, technical requirements, and reporting procedures. It is crucial to provide comprehensive training programs that cover all relevant areas to avoid knowledge gaps and mistakes. Attention to detail, especially in units and measurements, is of utmost importance. Even seemingly minor errors can have significant consequences. Engineers must prioritize accuracy and precision throughout the design, development, and operation of space systems. Continuous learning and improvement are vital. NASA's commitment to investigating failures, identifying lessons learned, and implementing recommendations demonstrates the importance of a culture that values continuous improvement and emphasizes safety and reliability in engineering practices. By understanding the challenges and lessons from cases like the Mars Climate Orbiter failure, Computer engineers can strive to develop robust, reliable, and resilient systems for space exploration and other applications.